Okay, so for this chapter 5, kita akan we will cover only 3 topics, okay? So which is Gaussian elimination method, LU factorization, and also the method to factorize matrices, okay? So I think the idea of Gaussian elimination you have might have learned during your what you call it, secondary school or during your foundation courses. It depends how much you learn about it, okay? And also after that, we are going to see alternative, how we can do also some to solve a linear equation, not by using Gaussian elimination, but what we call as a LU factorization and also method to factorize matrices, okay? So when we speak about linear equation, automatically it is actually in form of matrix or matrices, okay? So in this topic for this numerical method, we only consider what do you call it, linear equation or matrices in square matrix, okay? So if you have non-square matrix, you cannot solve using this method, okay? Square matrix means that you have 2 by 2 or 4 by 4, 5 by 5, and all must be in a square matrix, okay? So like 3 times 2 or other ununiform matrices, you cannot use this method, okay? So the idea is when you have some set of linear equation, you should be able to transform into a inner matrices, okay? So for example, you have this equation, right? So you have this form, and then it is being assigned by some coefficient or numbers where we assign as a, you can see it's like a coordinate, right? So a coordinate, and this our x is the value that we're going to solve, where we have solution of B, right? So we have all this set of linear equation, and we can transform it in terms of some matrix of A times the value of x equivalent to B. B is our solution, okay? So you can see that this is what I mean by A must be a square matrix, okay? And we are given by a coefficient by certain coordinates, okay? Because I and J will be assigned by row and column, right? So you can transform your A matrix in form of equation 5.3, and then X and B is equation 5.4 and 5.5. This is a normal, what they call it, matrix coefficient, or how we can assign in terms of all these values, right? So if we have unknown values, we should have some known values. Unknown values means that value yang we have to solve. Okay, that's why we say unknown. Unknown we don't know. We need to solve. Known value means that we know the value. Okay, so if you have so many unknown value, you cannot solve our problem, right? Okay, so when we speak about square matrices, then we can transform our matrix A in what we call as a tridiagonal matrix. Okay, so when we say about trigonometric, they have 3 elements. Okay, so they have a 3 diagonal, what we call as a contain as a non-zero element, right? So they have these 3: main diagonal, super diagonal, and also subdiagonal. Okay, so main diagonal is the one that in the middle. Okay, so for example, A11, A22, when A II is the value is the same, so this is what we call as a main diagonal. Okay, super diagonal means that this value, this range, the one that the upper of main diagonal, and then we have a subdiagonal. Okay, so this element is important when we want to do LU factorization later on. Okay, so we have to identify which one is main diagonal, which is super diagonal, and also which one is subdiagonal. Okay, super diagonal is also known as a what they call it, a U, and subdiagonal known as a L. Okay, lower and upper diagonal, right? So and then we can denote this upper triangular by a sign as a U matrices. You can see that below the main diagonal we make it 0. Okay, because why? This is to make easier for us to solve this linear equation. Okay, So when you have U matrices, obviously we have L. Okay. So when we see that we have some upper and lower matrices, the product of these two matrices must equal to our A. Okay, so the original matrix. Right. So when we have these two elements, we can easily solve no matter how much complicated the value in our matrices. Okay, but the condition is it must square matrix. All right. So next we move into Gauss elimination method. I'm sure that maybe you have seen before, maybe if you don't really understand it, but you have seen this form before. And usually we can rewrite our matrices in terms of augmented matrix. Augmented matrix means that this A prime, okay, and then a square bracket of A square bracket B, okay. So and then the augmented matrix is the expansion of the A and B matrices, okay. That is just in terms of writing, right? So the idea of Gauss elimination is we have to eliminate all zero element below the main diagonal, means that when I is the same value, all right? So, and then from there you can solve your Gauss elimination by using all those this operation, okay? So this idea is when you solve all those Gauss elimination, our idea is we're going to solve what is the value of X, right? So this is some example. I also have written example for this one in the separate PDF file. So in this case that we are going to solve some matrices given by A is equivalent to this form and this is our B, all right? So when you operate this augmented matrix, our idea is this 1, 2, and minus 1, we want to transform it into 0. Why? Because after that we can solve it by a backward substitution to get our x3, x2, and x1, right? So you can see here there is no x here, but x is like a hidden value, right? But there is that, the x value is there. Okay, so from there, we have to operate row by row. And for example, because this is the first value, 1 is the one that we are going to make it 0. So you can choose the row operation so that this value becomes 0, and you have to apply also to the matrix B. Okay, so that's why you can see all the value are changes. And you're taking this matrices, augmented matrix, and then you redo back again the row operation that the next row is 0. Okay, so the idea is we have to obtain 3 0 in our subdiagonal. Okay, and finally you operate another operation so that finally you can get this form, right? So here we just use some normal matrix operation where you just use this condition and to make sure everything becomes 0. Okay, so after that you will get your A double prime, which is now you can see your matrix in form of upper diagonal or upper matrices, right? So this is your U and this is your C, the new value of where we have simplified our B matrix, right? So when you solve all this thing, immediately you can solve what is the value of all your X, right? So by using backward substitution, you can see that at this part, this is X3 equivalent to 219 over 40. You can immediately get your X3, and then when you get X3 here, you replace back into this row, and then you can get X2. Then you get X2 and X3, you replace in this row, and then you can get X1. That is what is meant by back substitution to get all the solution. That is for Gaussian elimination, all right? So you can have this general formula of this Gaussian elimination, and this process can be done if you have non-zero element in your main diagonal. So you can see here our example. There is no 0 in our main diagonal. Main diagonal is 4, 4, 4. All right. So what happens if you have 0 in your main diagonal? So you cannot just simply apply this Gauss elimination and do it directly. So there is a process what we call as a swapping zeros. This is what we call as a pivoting. Okay, so pivot is a process that we are going to swap our row element, and then after that we can perform Gauss elimination. Okay, so we also have what we call as a partial pivot. So this for partial, we have only choose a column that below the current diagonal that we swap, right? So there is a two ways, all right? So it depends on how does your matrix look like. Okay, so this is algorithm for partial pivoting. So in this course, we're going to check for the partial pivoting. It means that we have only 1 0 in your main diagonal, and after that you have to solve it. So the idea is you check which column that have a 0 in the main diagonal, and after that you just swap the rows. Okay, so after that you just proceed like a normal Gauss elimination. Okay, so that is for the Gauss elimination. You know Gaussian, and then we have a pivot. Next, we have what we call as a LU factorization. LU factorization is actually the idea is come from the Gaussian, but the idea is they can do faster computation. Okay, so like Gaussian, you have to identify row by row and so on. But LU, you will just reduce the matrix into L and U, okay, and then after that you solve the solution. But you require one more step, which is you have to verify your L and U is equivalent to A. Okay, so if your L and U is not equivalent to A, so how you reduce or you decompose? The another word by reduce, we call it decompose. If not equivalent to A, then somehow your reduction or decomposition might be something wrong. Okay, so that's why you can see that we have to prove A equivalent to LU 5.12, right? So when you decompose into L and U, okay, so then your U will be depends on X, then you will get, when you solve this thing, this become some Y value, all right? So Y is actually going to be dependent on your L, so that you can solve for which is equivalent to B. B is the matrix that we have. Okay, then we solve all those things. After that, you can solve for all your X value, right? So you can see that there is a lot of steps, but this is good for the computational, all right? So this is how the ideal people do the LU factorization, especially if involved with the large matrices. For example, if you have 100 by 100 and so on. Okay, so if you have 100 by 100, by using Gauss elimination, it is hard for you to check one by one. So LU will be much faster to do, right? So the idea is very simple. You compute your LU factorization, and after that you solve this LY equivalent to B, and then you get your Y, and then your Y you put back into your U, and then you get solution of X, right? Okay, so when you have LU factorization, there are few methods to do this LU. The one that I've shown you before, that is what we call as a Doolittle method, right? So you can see we have few conditions here. We have Doolittle decomposition. Decomposition means reduction. So when you say decomposition, it means that you decompose into L and U. You don't solve for X yet, all right? So, and we have also Kraut and also Cholesky. Okay, the choice of decomposition will depends on your the condition of, for example, for Doolittle, it will depends on your lower diagonal. Okay, so where you have your lower diagonal, which is II, it means that this coordinate is the same. We fix into 1. Okay, so automatically when you see the matrix, we decompose it and you fix it to 1. Then others will start to do the matrix operation. For Kraut, you fix U, the upper diagonal. Okay, I mean the coordinate is the same. This is we fix it to 1. But for Cholesky, this is a bit special. This one is you have to identify your Lij and Uij. The value must be the same. When this is the same, So all the coordinates that, for example, Li and Uii, you have to do the matrix operation. This is how we decompose the matrices accordingly. All right. So you can see here, usually Doolittle and Crowd is the most popular people to do by hand. Cholesky is popular to do by computational because this is far more complicated process, right? And here in crowd decomposition, we have the column and row are alternate, right? So when it's alternate, what happens is they will alternate the solution. If you see Doolittle that we done previously, we alternate it in so that we can get our matrix A back, okay? So here is the algorithm. You can read through it. And next is I'm going to show you the example that I've given to you previously. Okay, I hope you check this example too. Okay, so when you have the example 5.1, you can see that I highlighted. So usually we're given by this form, yeah? So we have some form of linear equation. Immediately you have to transform into a prime like here, okay? So, and this part that I highlight, the yellow one, is where we're going to transform into 0. This is for Gauss elimination, right? Let me see, is it possible I make it bigger? Or, all right. Make it squarish, okay? So when we have this value, you can see that we can do the matrix operation, okay? And then we can solve by using backward substitution, okay? So then, example 5.2, okay, by using the same example by 5.1, we use the same matrix, but here you can see that I put the main diagonal is 0, okay? So from there, you have to identify how to swap the matrix. Okay, so a few of your friends just enter the Google Meet. All right, so you can see that we transform this matrix. You can see that we do some row operation. We swap with R2 and R3. Okay, so from there, we can perform the normal Gauss elimination. You can see that now our 0 is no longer in the main diagonal. It's going to become at the lower part, right? So you can see that when you transform this, okay, so it means that this one is also being transformed, okay? You don't see the difference because it have both the same value, okay? So if you don't have the same value, you can see that it is transformed into this row swapping, right? So after that, you can see that how we choose the Gauss elimination is a bit different from example 1. Obviously, because the value is now different, okay? So from there, you can see that first we transform it become 0. And you can see that the 0 here, when you do the operation, it become value back, okay? Don't worry about that. You just do another operation to make it 0, okay? So this is the idea where you can solve it and immediately you can get, by using backward substitution, you can get back the value, okay? So another thing is, for example, if you have an unknown value of in your matrices, okay? So example 5.3, so for example, you have some epsilon, you have to find what is value of epsilon when we know that epsilon should not be 0. This is actually people do when you want to test if there is a singularity or not in your coding, right? So for example, if you're going to solve this problem, so you expand the value of your x and x2, okay? X and x2 is given, they should give some equation, and this is your equation, these two, and then you have to expand it, right? So what is O here? O is order of what? Order of 1 or 2 or 3. So in this case, since epsilon is unknown, it is order of epsilon. Okay, so epsilon is also known as a machine epsilon, a machine number. Okay, so when you expand your value of x, you expand using the Taylor expansion, right? So when you expand, obviously the higher order will produce zero value. Okay, so we retain until the first order. If you can see all this thing, when you retain the first order, we find that our epsilon both has value of 1, x1 and x2 1 when you try to expand it. Okay, so this is estimate. We estimate the value because in computational we cannot get the exact value, but we only can get purely estimated value, right? So after that we can test. This is our first test. Second test is we use Gaussian elimination. Okay, we transform our equation here into matrices. You can see that it's a linear equation. We transform the value into matrices, augmented matrix. Okay. And then we can perform some Gaussian elimination. When we perform this thing, and then we get the solution, what happened is the estimated value for x2 is okay, but for x1 is not okay. Because why? We estimate x1 should be 1. So how to solve this? That's where the pivoting or partial pivoting will come in place. We just swap the rows. Remember the epsilon is unknown value. Okay, when we swap the rows and then we solve the Gaussian elimination back again, we obtain that x1 and x2 similar to the value that we estimated. Okay, so this is how we try to find the solution of our estimated value, right? So this is, for example, if we have a physics problem, you know that the value should not be 0. So this is how we can make a test, right? Either it will goes to 0 or not. But this test is good if you have a very what do you call it? Not a big matrices, right? So you have a small matrices, you can test like this easily. But if you have bigger matrices, you have to solve it by computational, right? So this is for the first one. So the next one is where we're going to solve for your LU. So LU is, you can see that here you are given by matrix A, B, and X, right? So this matrix you have to decompose or reduce to become L and U, okay? So you can see here we decompose into L and decompose into U, okay? So product of L and U, you should get back your A, right? So how to decompose this? Decompose this, you have to follow the factorization method that we have discussed earlier, okay? So in this case, it's just a normal, what do you call it, LU factorization. You can use, for example, Gaussian elimination first, because what LU means that? LU means that you have to fix this for L, this value is 0, and for U, the lower one is 0. Order definition is, what do you call it, different, but L means that all the upper value has value. The lower value has value. The upper is 0. So for you, the lower value is 0, but the upper value, you have value at the upper diagonal, right? So you can see here, we make it 0, and then we can do the LU factorization. Okay, so I don't show this step, but you should, you can have a try. What you should do is, first, you just make a blank matrices. It means that you put your L0 first, and then you try to eliminate all this row and column so that it will fulfill the value, okay? So then you have to prove. When you prove it, it should get back into A. Okay, you can see that you have L now. So L is now your matrices that you be reduced, which is equivalent to the value of B. What is B? B is this one. Okay, so then you can get the solution of Y. Okay, so when you get the Y, you can see this is your Y solution. And you put back your Y into your U matrices, and then, okay, so this one is technically will replace as your B. Okay, so Y become your B. You solve it, and then you can get the solution of your x3, x2, and x1 by using backward. So this one is you using forward, and this one you using backward. The idea is just the same thing. Forward means that you solve for y1 first, then you move on to y2, y3. Backward means that you solve by the largest value. In this case is s3, and then you solve s2 and s1. That is backward. All right. So when you next we see the Doolittle method. This is the general one. Okay. So this is, we don't say any method. This is a very general method. You just put the lower and upper, and then you put 0, and then you simplify all those other matrices. Okay, so when you have some specific method, Doolittle for example, then we have to rewrite our coordinate. Okay, so this is the L, and this is your U. Okay, which is equivalent to your A. Right, so you can see that I put some coordinate for your L and U, so that it's easier for you to see. And from there, this is the condition that we put to what do you call it? To fulfill the condition of Doolittle. Okay, so in Doolittle method, it says that Lii equivalent to 1. So we have to identify where is L11. So this is our L11. Okay, so L22. Okay, these are the two conditions. So that's why immediately this L11 and L22 must become 1. Okay, so what happened is now immediately you can write this is 1, this is L21, this is L12, and this is 1. Okay, just to show you how sorry, this is U. Right, so these are being replaced by the value. So that's why when you replace the value, you can immediately do the matrix operation just like below here. Okay, so when you do the matrix operation, the idea is you want to get what is the value of L21, L12, because it's an unknown. Okay, when you do the matrix operation, you can get the value of your L21 and L12. Similarly for U. Okay, so by using matrix operation, you can see here, we can put all the values. So for U, immediately, we know that this is 0 without do any operation. And for L, this one is 0. Okay, so after that, you verify. So in this example, you don't solve for X because you are not given B. Okay, when you are not given B, you just do decomposition, means that you reduce the matrix. No need to solve for X because there is no B, right? So this is how you identify different decomposition method. Okay, so then we have another method which is crowd, right? So crowd is again, we have to write our matrices back again. This is your L and this is U. Okay, so before we build any value, we immediately create what do you call it? Oh, sorry. I hope I don't mess up this thing. I do mess up. Okay. All right. So we make it as a 0 first. Okay. So when you do all this value, then you put all the coordinate, right? So when you do the coordinate, then we can do the matrix operation, row, column first, and then a row. Okay, so this is the idea for you to reduce it. You can see the crowd is a bit crowded. It's a lot of step, right? So this is the idea you can reduce, and finally you can get what is your L and U. Okay, again you have to verify the matrices. If you do the same matrices by using different method, you can see that your L and U might be different. Okay, because of the condition. Remember, for crowd, your UII is 1. Okay, it means that now you can see here, this we fix 1. Okay, so for first you fix which one is location of 0 in L and U matrices, and then you apply this condition. Okay, so when you apply this condition in a U matrix, after that you can solve for your row operation by using the normal step. Okay, so this is, we just purely decompose. We don't solve for X2, right? Decompose means we reduce the matrix. Okay, so that is the first part of the lecture. Okay, the second part of the lecture is I want you to run a code for this Gauss elimination, right? So first, you should able to do by hand, and after that, I want you to solve using code. How to do that? Okay, I stop this one first. Where is my browser? Oh, it's here. So I hope all of you have visit my GitHub account. Let me Windows. Okay. Can you see my GitHub now? Right. So when you see my GitHub account, I have several code here. Hold on, someone is entering the Google Meet again. Oops. Do you listen to my voice?
Yes, doctor.
Yes,
Okay,
doctor.
because it show that the mic is off. Okay, so I have several code here that I've written for this class. For this semester, you only use bisection for chapter 4, bisection, Newton Raphson and secant for chapter 4, and also Newton optimization for chapter 3. So for chapter 5, I create one what we call as a linear.py. Okay, so you can clone it, or I think you have to clone. Clone means that they will make a copy to your local desktop, or you can just, if you really don't know how to do it, you just select all and then paste to your Anaconda, that is the most simplest thing to do, right? So here is the Gaussian elimination code without using any modules. I don't use any modules except for numpy. Numpy ni because I want to call array. Okay, so after this, I'm going to show you how to use modules, all right? So it means that this is, I do it from scratch by hand by using the algorithm given. Okay, so how does it look like? How does it works? So first, I have to you have to put your input. Okay, so you, in this case, our input should be a square matrices. Remember that. And then you have to, because Python, it works by rows. Okay, it doesn't work by columns. So that's why you can see this matrix you have to put in this kind of rows. I mean, this is first row, second row, and third row. This is 3 by 3. And after that, this is your, what is your B matrix. Okay, so because why we are, this one we're going to solve for X. So I define what is Gauss elimination for A and B. A is our input, A and B is our input. And after that, I have to define the length. Remember, this is square matrix. So N is the length of your matrix, which is, I can check what is from B. Okay, so you have 3. It's easier for you. If you define for A, nanti they will see that 3 by 3. So you just want to have a single digit, right? So we solve for, I choose for D, all right? So now we're going to do row operation. Okay, so remember that we have I and J, right? So in this case, we check that for the J coordinate in range of 0 until n minus 1, this is the coordinate in the matrix. And from there, we can calculate your Gauss elimination first part, right? So since we're going to solve for X, you have to create some entry matrices for X. So that's why there is X numpy zeros. Means that we are going to create some empty bracket for us to insert our answer later on. Okay, if not, they have no idea where the X should go. Okay, so that is the idea of this what you call it, coding. All right. So we have to do operation of A and also B. What is lambda? Lambda is the how they do the row operation, the coefficient that we get, and from there they will calculate the row operation. Okay. So then they move to a different coordinate, and then they solve for x. Okay. So finally, you can solve what is the value of you minus, this is like a backward substitution. And finally, you can get your x. When you run the code, it will give you the answer of what is the value of your x. Okay. So that is how you can solve a linear equation without modules. What are the modules that I'm talking about? Okay, I saw some of the exercise that you have shown me before for previous chapter. Some of you use SciPy and so on. Okay, in this level, I try not to introduce you for SciPy first because I want you to have the idea how to do code, right? But for chapter 5 here, I'm going to introduce you SciPy only to solve for pivot and also to solve for factorization. Because why? The way you want to control the matrix will be much tedious. For Gaussian elimination, this is what we call as a naive Gaussian elimination code. Naive means that simple. Okay, so when you solve for more complicated matrices, okay, so it requires for you to play around with these indices, which is, I see that Python somehow have some problem for you to identify. If you choose the indices incorrectly, what happens is you will get the wrong result. Okay, so I'm going to introduce you what we call as a SciPy, right? SciPy is a module, what we call as a scientific Python. This is also have the Gaussian elimination, but for Gaussian elimination normal one, I want you to use this one. Okay, so this one is only when you want to use, for example, LU and also pivot. Okay, so pivot is a bit tricky because you have to identify which row. For example, if you have row is everywhere, row 1 or row 2, both of them that has a pivot. So the idea of how you want to interchange the indices might be a bit complicated for you to do it at this level. All right. So I will give you what does this SciPy do. SciPy is a scientific Linux. What they do is the code like this is actually hidden. Okay, it's hidden behind the scientific Linux, scientific Python, and you just run as a black box. Black box means that you don't have to know all this thing. But in science, that's why we learn numerical method. You should know how to do this. Because why? Behind this scientific Python, there is people who knows how to do numerical coding. Those are the one who provide the code behind it. Okay, for example, okay, we go to the first page. Okay, so this is, you can just find the SciPy Linux. Okay, so this is what we call a linear algebra. The one that we learn now is a linear algebra. Okay, so we have so many what we call modules for here, the function, right? And all these are coming from the numerical method. Okay, some of them you don't learn because this is for the higher level of numerical method. Okay, so usually we learn in the computational physics later on, right? How to do this thing. Okay, and it cannot be used by hand. You have to do computational, right? So for you, okay, so it's either you use this solve. Solve is similar like the Gaussian elimination, okay, or soft banded. Okay, soft banded or soft H banded. This is just the same. The idea of they play around with the indices is different. Okay, but for this class, I want you to see what we call as a decomposition. Decompose. This is the one that LU. Okay, so in this code, they use purely Doolittle. Crowd is not available here. They only have Doolittle and Cholesky. Okay, crowd, they don't do it yet because it seems that they use Doolittle is the easiest one. So we have, they already include the pivot mechanism so that you can easily solve about, you just give the matrix and then you solve for the pivoting and then they will compose the LU. Okay, so this is LU. They have to immediately get the LU, and then LU factor is they factorize it. They can produce what is L and U, and I think this one is they just calculate directly what is the value of X. Okay, sorry, no, X is no. This is LU soft, and this is also the same thing. Both of them. Maybe how they do it a bit different. And then we have LU soft. It means that they factorize first, and then they solve by this X. Okay, this one is without X. Let me see. Yes, this one, how to read this thing is, they say that there is SciPy Linac LU factor. And these are the conditions that you have to put. A is your matrix, override A force check finite is optional. Okay, so what does it mean? It means that it will decompose a matrix of A with a some value P, and this is your L. Okay, so P is some pivot value. If you have some zero in your matrix, they will activate this P. If not, they just calculate your L and U. Right? So first you have to put inside the A matrix. Okay, this is just optional, and then they will produce your LU. In this case, there is no B. There is just purely decomposed. Okay, so and then they will produce the LU matrix, right? And also they have some pivot indices for the permutation matrix. Okay, and these are how you can run it. Okay, so what you can do is you just open your, what they call it, Anaconda or whatever editor that you want. You just type it. So I'm showing you how to do this. Okay, so I'm going to share my all the screen, my entire screen. Okay, so I'm going to open some terminal here. Okay, so do it here so that it will be faster for you to see. Okay, I just open some value from here. So for example, you want to solve for LU, what they call it, Linac. Okay, so I just put like this, LU dot U1. Okay, so how to, I hope you can see both, both of my screen. Okay, so how to do this? You just, if you have your Python, you just type it from scipy.linac import LU. Okay, so then you have to put, if you want to make it easier, you just can copy and paste. It's the same thing. But do not copy the arrow here. Yeah? This arrow here is for the interactive Python. So you can run this thing and see that how does it look like. Oh, sorry, I have to import NumPy. Okay, so from here, it will factorize your LU and PV. Okay, so if you just want to see your LU, you just print your LU. The PV is just your pivot. Okay, so this is the value that they have decomposed. Okay, and this is by using this LU factor. Okay, so another one is you can so you want to see what is the code behind it, you just click source. Okay, so these are the source that the people have contributed to write the decomposed LU. You can see it's a very long code because they're going to make it general. So technically, your task is to do something like this, but I realize it will take some time for you to do all those things. So it's okay. We just use for this SciPy for this moment, for this for this section for LU. Okay. So another one is I want to show you. You're going to use this LU solve, right? So LU solve is they can solve for value of x. And just now it's just purely decompose of L and U. It does not produce your L. Okay. So from here, all right. So here they have another example. They use LU factorize the matrix. This is LU, linear LU, so the matrix. So you do the same thing, but in this case, they import two things, LU and LSOF. Just now they import only one module. Okay. So all these modules must be embedded in this SciPy linear, right? So you have to produce, you have to edit for your A and B, and then you just type LU pivot, and then you can get your X value. Okay. So then if you want to check the LU equivalent to A, you can use this command. Okay. So numpy all close of A times X minus B, numpy 0. This will produce you the, what do you call it, will check your solution. Okay. So if it's true, it will give true. If you have something else, they will give you false. Okay. So this is how you can do for the linear equation. Quite straightforward. Okay. So the next one is I want you to do your tutorial. Okay, I stop this one first. Stop sharing. I share only the tutorial file.